Led by the Aerospace Technology Institute and backed by the UK government, FlyZero is a one-of-a-kind research project aiming to realise zero carbon emission air travel by the end of the decade. A team of experts from across UK aerospace and academia is working to develop the new technologies that we will need to propel the next generation of aircraft into our skies. And by fusing these technologies together to create and evaluate a fleet of groundbreaking new concepts, ATI FlyZero is defining a truly sustainable future for the aircraft, airports, and airspace of tomorrow. As the global aviation industry looks to a brighter, greener future, FlyZero will help the UK stand at the forefront of sustainable flight in design, manufacture, technology, and skills for years to come. A new dawn for aviation is on the horizon.
Good afternoon and welcome. Thank you for joining us at FlyZero. I'm Chris Gear, Project Director. The technologies and development scout aircraft you've just seen in our opening video offer a snapshot of our wide-ranging, independent and blank canvas exploration of the Zero Carbon Commercial Aircraft Challenge. During today's webinar, you'll hear more about these technologies and see more of our scout aircraft, which reflect the progress we've made in the first 7 months of the project. Today, you'll be hearing from Simon Webb, Chief Engineer, Propulsion, Tim Goldsworthy, Chief Engineer, Airframe, Naresh Kumar, Head of Sustainability, and Mark Howard, Head of Commercial. As well as that, Dr. Katie Milne, Head of Industrial Strategy, will be hosting our event, including the Q&A, which is coming up later on. As a brief introduction for anyone not familiar with FlyZero, we're led by the ATI and backed by the UK government. FlyZero is a one-of-a-kind research project aiming to realise zero carbon emission commercial aviation by the end of the decade. We're bringing experts together from across the UK to conduct a detailed and holistic study of the design challenges, manufacturing demands, operational requirements, and market opportunity of potential zero carbon emission aircraft concepts. In the coming months, FlyZero will use the findings from the Scout aircraft we're sharing for the first time today to develop 3 final aircraft concepts. Together with the technology roadmaps, market and economic analysis, and life cycle sustainability assessment, these will support the UK aerospace sector in standing at the forefront of sustainable flight in design, manufacture, technology, and skills year to come. Team FlyZero. We are fortunate to have a world-class team of amongst 100 engineers and aerospace professionals with a shared passion for addressing aviation's carbon challenge. The team is working fantastically together in these difficult times of COVID in a remote environment, and I can't thank them enough for their energy and commitment to this cause. And thank you to our contributing organizations for your support to the FlyZero project. Without all of this, it wouldn't be possible. As part of today's event, we will have live Q&A, an opportunity to ask questions to any of today's speakers. To submit a question, please scan the QR code on the web page or visit Slido and enter code 902188. You can also join the conversation on Twitter using hashtag FlyZero. I'll now hand over to our first speaker this afternoon, Simon Webb. Thank you.
Hello, my name's Simon Webb. I'm the Chief Engineer for Propulsion on FlyZero, and I'm seconded in from Rolls-Royce. Today I'm going to talk you through an overview of FlyZero, the programme and our mission statement, and specifically talk about the fuel comparison and selection study we've run, where we've arrived at the finding that liquid hydrogen could be the key fuel to help us unlock zero carbon flight for the future. So our mission statement is to study the options to help us realise zero carbon emission commercial flight by the end of the decade. And this study has been initiated and led by the Aerospace Technology Institute and is backed and funded by the UK government. How are we addressing this significant challenge? Well, we've assembled a large group of industry experts, nearly 100 people now, from the contributing companies you can see here, and a number of independent experts we've brought in to complement the team as well. And this is a holistic study looking at the enabling technologies, how we would put them into a number of Scout aircraft that we've studied. We're looking at the marketplace, the economics of how we could bring this to market, and what the business case would be to operate such an aircraft. We're considering the sustainability picture. We're looking at developing the environmental science, not just for CO2 impact, but the other emissions like NOx, like contrails, and the effect they can have on the environment and on global warming in the future. We're considering the current UK capabilities, where we can build on strengths, and where there's gaps and we need to take tangible action and invest in UK capability for the future. We're also looking at the ground infrastructure challenge around what we would need to do in the future for fuel production, fuel distribution, and what we would need to do around airports to store such fuels and to allow safe, rapid turnaround times for refueling so we didn't adversely impact aircraft operation in the future. We've begun this study at the beginning of this year. We've now extended it to the end of Q1 next year, and we hope to elicit interest from government and with industry backing to be able to carry on and mature these technologies in line with the roadmaps we publish after Q1 next year. We looked at the marketplace, and here you can see an assessment of how the marketplace currently is split in terms of capability and sector distance. And when we look at these three sectors of regional, narrowbody and widebody, you can see both against CO2 emissions and against market revenue, there's a real need to address the narrowbody and widebody parts of the market. And a significant range aircraft, if we could get an aircraft of around 5,000 nautical miles, could cover the whole globe with a single stop. And we think there's a real need then to have a strategic solution that has significant capability in terms of payload and range. To start to assess the options to address that significant challenge, we've done a fuel or energy comparison study looking at these different options against different attributes. Now, when we look at CO2, part of the core mission statement, all these green options here could address a zero CO2 emissions aircraft. SAF we put on here as a comparison. Sustainable aviation fuels could provide a route through to a net zero solution in the future as well. We're considering NOx emissions as well as CO2. Batteries, fuel cells are very powerful in this. They could deliver a zero NOx solution. Combusting liquid hydrogen in the future, if we can intelligently design and develop a combustion system around that, we think we could develop a significant reduction in NOx capability for an aircraft. Ammonia, we think, would have a significant challenge in NOx emissions. It would inherently be much harder to design a low NOx ammonia combusting system, we believe. Contrails are a significant challenge and can have a significant contributing effect on global warming. So we're doing a lot of work to understand the formation of contrails, how they get formed, how they persist, and how we avoid the formation of persistent contrails in the future. Now, hydrogen, if we combust or put hydrogen through a fuel cell, will produce more H2O, but compared to kerosene and SAF, won't produce the same type of particulate matter, which can form persistent contrails. So we're looking at the balancing effects here, working with academia on understanding better how we avoid persistent contrail formation in the future. When we consider the volume of fuel, we think batteries and gaseous hydrogen have a significant challenge here. They're large for a given amount of energy. Less of a challenge, but still to be addressed, are these other fuels, so liquid hydrogen, ammonia. There's more we can do to assess these and deal with these at aircraft level with the fuel volume challenge they give. And critical here is fuel and propulsion system mass. And again, batteries and gaseous hydrogen have a significant challenge here. Batteries need a real improvement in the future to become competitive at significant range. And we don't see that coming on the technology horizon sufficiently to justify them to being on a significant range aircraft. Hydrogen, although it is light itself, is very large. And when we compress hydrogen to very high pressures, you then need a very thick, heavy pressure vessel around that hydrogen if it's gaseous. So we don't think that's feasible. Also, ammonia doesn't really have the energy density to be able to do significant range as well. So that's pulled us back towards liquid hydrogen. We believe it's a very light fuel, it's very energy dense. We're considering how we put a powertrain solution around liquid hydrogen, and we're looking at both combusting liquid hydrogen in a gas turbine and putting hydrogen into a fuel cell as well. We've seen there is some thermal management challenge with the fuel cell, but with the team we have, the capabilities we have in the team, we're getting to a position where we think we can address that thermal management challenge going forward. Now, the investment, both in terms of onboard technology and ground-based infrastructure. Now, liquid hydrogen provides a real key strategic capability for the future, but we recognise there's a real need to invest to make that happen. It won't be quick. It will need significant investment and capability development across the industry. And we're trying to elicit the backing to make that happen. And so the UK can play a significant role in that in the future. And lastly on here, fuel cost. This is another reason we think liquid hydrogen is a good option for the future. We think that there's a route through to reduce the production cost of liquid hydrogen and make it a feasible fuel for the future. And it's lightweight and then relatively affordable. So we think liquid hydrogen is a lightweight, relatively affordable fuel, and in being so, the best route to a green strategic capability for aviation. We recognise there are significant challenges here. Green liquid hydrogen production and distribution needs to be invested in and ramped up. We're talking to the Department for Transport and to industry about how this could happen. To give you a feel for the scale of challenge, Heathrow alone in 2019 was using 22 million litres of kerosene per day. And we need to address the safe and rapid refuelling. We've assembled a multidisciplinary team on FlyZero to focus on this challenge, to come up with solutions to allow this to happen and not adversely impact aircraft operation in the future. The UK technology and capability, we need to rapidly understand and then build and improve our capability in key areas, spanning across hydrogen storage on board, cryogenic systems, fuel cells, heat exchangers, and hydrogen combustion. And we need to do this in order to compete with what exists and is now being developed in France and Germany as an example. And I'm sure there'll be other investments around the globe as time moves on. On the sustainability front, we're looking at, as I said, the understanding and the science behind the formation of persistent contrails and how we mitigate and avoid that in the future. We're also looking at the science behind hydrogen combustion, the technical risks there, and how we design a system to minimise the formation of NOx in the future. And we think there's real opportunity to do so. And we've bolstered the internal team by significant academic collaborations there. We're also looking at the policies, the regulations, the certification framework, how that fits for a hydrogen solution and what changes might be needed for the future and what challenges there are. So the team's working with the CAA and HSE and how we better understand that and what action would be needed in the future to inform those regulations and things like the acceptable means of compliance in the future. Now to the propulsion technology bricks. obviously there's a significant amount of technical challenge and novelty that would need to come into the energy and propulsion system in the future. So starting with understanding how we would have a lightweight, safe, robust liquid hydrogen tank on board that was insulated, could deal with the risk of boil off and minimize that risk in the future. And then a hydrogen fuel system and all the cryogenic equipment, instrumentation, the architecture, the control system to go around that whole system and deliver the necessary amount of liquid hydrogen and control the characteristics, the pressure, the temperature of the liquid hydrogen and the supercritical hydrogen through that system. That would need to go into a thermal management system. We will need to increase the temperature of that hydrogen at some point through that system, and we'll need heat exchanger technology to allow us to do that. And we'll need that technology to be robust, lightweight, and compact. Now, one powertrain solution is we then put that fuel into a gas turbine. So as I said, we're understanding the science and the challenge in the fuel system all the way into the gas turbine and then the combustion subsystem. The other option is to use fuel cells. We're looking at low temperature PEM fuel cells here and the electrical system that would then go around that and the thermal management challenge of the heat rejection from a fuel cell. And so additional challenges we're considering where we need to develop is around power electronics, high power dense motors, and then the generation of thrust on the end of that system as well. So our findings and way forward, as I've shown you, the FlyZero team has completed our first assessment phase now. We've completed this comparison and selection activity on fuels, and we're looking at the marketplace and the need to attack as quickly as possible and in the biggest way possible the current CO2 emissions from aviation. We believe there's a need for significant range in a strategic solution, and that liquid hydrogen offers the best capability to address that for the medium and long range aircraft. But that this will require a major investment to deliver the technology and the infrastructure on the ground to enable that. And that this comparison piece we've done, we're going to publish a paper shortly which will flesh out some of the logic I've been through here. We'll publish that, we'll put that out into the industry, into the public, so everyone can see what we're looking at. And we want to be open and share our logic so people can see what we're doing and why we've picked liquid hydrogen as what we believe is the best solution for the future. So the team are now exploring some of these challenges, how we go and address these. We have a key focus on the onboard technology and the capability in the UK and how we would develop these in the future from the roadmaps we will derive through this study activity. We're working up a route through to demonstrate safe, reliable hydrogen-powered flight in the future, and a particular key challenge here is the safe, rapid refueling and turnaround capability. We believe there is a place for SAF still, alongside liquid hydrogen, as this can quickly provide a route to a significant reduction in carbon footprint and the extension of existing aircraft life without a major refit. And a hydrogen solution would require a new aircraft in order to maximise its capability. But production on SAF, like liquid hydrogen, needs to be ramped up and investment needs to be had there to enable that to happen. So we're now starting to look at what the follow-on activity could be after this study phase. There's more work to do still in the study, but we're starting to plan out what we'd want to do afterwards. How would we think about developing these technologies? What would we need to do to mature the understanding, the scientific modelling behind them? Where would we need to go and do testing in the future in order to inform that? And we want to collaborate. We want to collaborate throughout industry, throughout the catapult centres and research organisations, and in academia, and obviously with government as well. We want to pull together a coalition across all these different options to make green flight solutions real in the future. And in doing so, enable guilt-free flying in the future to allow people to continue to travel, to continue to explore the world, to continue to meet face-to-face and operate businesses and build trust together in the future without the negative impact on the environment. Okay, thank you.
Good afternoon, everybody. My name's Katie Milne and I'm the Head of Industrial Strategy for FlyZero. I hope that you all enjoyed that introduction from Chris Gear, who's joining me now, and that overview of fuel solutions from Simon Webb. Really, unfortunately, Simon's off ill today, so Chris has come back to answer some questions that I'm going to put to him on the fuel section for the next few minutes. And then after that, we'll move on to a talk from our colleague Tim Galsworthy, who's one of the chief engineers on the programme for Airframe. So, welcome back, Chris. I hope
Thanks,
you're looking forward
Katie.
to being in the hot seat. I feel like this might be a once-in-a-career opportunity to interrogate my boss, so but hopefully it will go okay. So Simon's presentation was really interesting. You know, he's clearly singling out liquid hydrogen as having potential for future aircraft. Overall, the aviation sector has got an incredible safety record, and the flying aircraft technology has been based on kerosene solutions which have been developed over many decades and incrementally got safer and safer and safer. How do you think we need to approach the potential risks of changing to a new technology and especially changing to hydrogen?
Okay, thanks, Katie. I mean, if you think about hydrogen, it is actually used safely today in defense and space sectors, and liquid hydrogen is being transported via tanker, ship, and pipelines today. So it is actually being used in the countries that we operate today. There is, however, significant differences in the technology and design challenges driven by the aerospace regulations and reliability requirements and the safety. So the FlyZero team is identifying those differences and exploring how these can be addressed going forward. There will require substantial investment and work, but we fundamentally believe it will be possible to enable hydrogen-powered flight safely and reliably. But it's going to be a challenge for everyone in the aerospace community to make that happen.
So is it something that can be solved by engineering solutions, do you think?
I think it's going to engineering solutions. It's definitely solvable to fly a hydrogen-powered aircraft. There are some military small vehicles flying with hydrogen-powered. So I think the issue is going to be around the safety and the regulations. So we'll need a lot of regulations in place to ensure that the hydrogen is kept and maintained properly within the aircraft, and all the commercial operational conditions are met to protect the passengers. So it will require new regulations that probably don't exist today in the EASA, FAA, CAA authorities.
So it sounds like there's quite a lot of work to be done. What do you think the timeline is to take these new aircraft to into reality, and what are the key milestones along that timeline?
Today, we've got a really tight timeline. We need this zero carbon emission vehicle in operation ASAP to protect the environment. And what I see the challenge is actually how do we get to that technology readiness? And I think what we need to be focused on are the bricks that actually make up these technologies and getting them ready by 2025 so that they could actually be developed to be fitted onto a experimental aircraft to begin with, but also headed towards a commercial aircraft. So we'll need substantial government investment and industry support to make this happen, because it's not only the aircraft that we're going to have to develop, it's all the infrastructure to support that particular fuel at the airports, in the industries to manufacture it, and actually in the overall infrastructure of the electrical systems that we use to generate such things as hydrogen. So a key enabler will be the hydrogen production and airport infrastructure investment alongside the aircraft. We'll need to feed into this. Sorry,
you talked about 2025 for technology readiness. You talked about 2027 for flying test. When do you think aircraft might enter into service?
So yesterday, Airbus were talking about this, and they are focused about bringing an aircraft into service by 2035. And I do believe that is very doable, but it will be a colossal investment in all the things I've just described. But there's nothing that technically can stop us. It's more about the investment and the commercial economics that will be one of the key challenges. But you've got to look at it as, we're actually doing this to protect the environment, and we've got to look at what that cost means against that issue.
And given these quite long timescales, so 2035 is 15 years away, and there's a big climate change imperative, aviation must decarbonise. Are there other stepping stones to zero carbon or net zero carbon by 2050?
So there are other things that can be done. There is sustainable aviation fuel, which could be used as one of the stepping stones to help us reduce the amount of carbon we're putting into the atmosphere. There could be things around extracting the carbon out of the atmosphere, but all these things also need infrastructure and investment to bring those to fruition, because at the moment there isn't enough capacity to make the sustainable aviation fuel needed. So it is going to be taking these stepping stones from where we are today with kerosene to some form of liquid hydrogen solution to get to zero carbon emissions. And that's going to be the challenge for all of us, not only the industry side, but the government side, the legislation side. But more importantly, it's about bringing everyone's focus on this is the only way that we can succeed in meeting our 2050 CO2 targets.
Okay, that's brilliant, Chris. Thank you very much. And thank you to Simon for his presentation. It's a shame he couldn't be here this afternoon. We're going to pass on now to Tim Goldsworthy, who's our Chief Engineer for Airframe. And we'll just hand over. Thank you.
Thank you, Katie.
Hello, everyone, and thank you for joining our webinar today. I'm Tim Goldsworthy, and I share the Chief Engineer Airframe accountabilities with Mark Willier. And I'm going to take you through our approach to the technology bricks, the workflow we've used to understand those bricks, and how we're starting to integrate them now into aircraft level solutions. I thought it would make sense to start with our general technology workflow throughout the year. At the beginning of the year, which is still a relatively small team, we naturally had to focus on the key enabling technologies in terms of fuels and energy systems which could meet our zero emissions targets. And regardless of the individual capabilities we brought to the project, or indeed what team we're allocated to, everyone on the project focused on that activity. In phase 2, once we had that understanding and had also completed our main recruitment phase, we were able to expand that work and start looking at the integration challenge of those technologies. And from that, then move on into phase 3, where we began to look at aircraft level definitions which could support those objectives, and also expand the work outside of the team and really start pushing external work package with academia and industrial communities, which I'll talk a bit more about later. And where we are now is in about a third of the way through phase 4, where we've now completed assessment of a whole range of different aircraft, with some of which you've seen in the video at the beginning today, and I'll talk a bit more about on subsequent slides. We're starting to refine that understanding into 3 concept aircraft to really focus much more on specific geometrical and architectural solutions for our chosen technologies, as well as completing the full range of work packages we've allocated. But also now, I guess, we're starting to think about the end because of this particular phase of FlyZero, because we have to now start in the months ahead drawing our conclusions, framing our key questions, and proposing the next priorities of a follow-on activity. So beginning to look at producing those reports to be validated and officialized in the first quarter of next year. So the scouts, you've seen the video at the beginning, and you can see there a number of our scout images, from relatively conventional through to quite unconventional. And I think I can hear your brains going over from here already, because if you're in this industry, you tend to be passionate about aircraft. And as soon as anyone produces an image of a concept aircraft, you immediately start thinking about advantages, disadvantages, opportunities and risks against them. But I think it's a key recurrent theme you're going to hear from me in this presentation that those aircraft have been defined not as specific individual solutions, but as integration vehicles for the understanding of the technology which will enable zero emissions. The final and optimized design of a specific aircraft solution is for the future. We're trying to build bottom up our technology understanding for zero emissions objectives, but also with a nod to top level aircraft definition as well, such as some topics like certification, as an example, you do need to consider top down. So the Scouts that we developed in phase 3 fell into 3 main categories: a regional version you can see on the left, a narrow body version in the middle, and a mid-size version on the right. 27 in all, and once again some radical configurations. And just by looking at the configurations, I'm sure we can realize that the primary driver of those shapes is in fact the integration of the propulsion system and the integration of space and tank sizing for holding a novel fuel. On the existing kerosene fleet, obviously the fuel is in the wings, and that's an incredibly convenient location, both in terms of available space and mass center of gravity management. A lot of these new energy systems, the fuels, don't lend themselves to using that space, so there's a bit of a radical approach needed to how we manage to maintain range, payload, and classic mission profiles for these sorts of aircraft, but also accommodate potentially the fuel tank in different areas of the aircraft of what we've traditionally done. And some of this may drive radical configurations. We may find a way of doing it on more classical configurations, but those were the sort of things we were trying to consider in defining these Scout aircraft. But once again, as a way of integrating key features and learning from them, as opposed to specifically optimizing one of those versions. So there's a bit more detailed example on the technology bricks themselves. Just 3 examples. On the left, you see a classic aircraft from today's fleet, and you see some from the knowledge we have today, sizing of different fuel capacities that have to fit on the aircraft, and that's a 1-to-1 scale. And you can see if the fuel's not in the wing, then you would significantly compromise available space in fuselage, hence the more radical configurations or different shapes we would require. A bit more detailed architectural work in the middle as a blended wing body, looking at actually specifically allocating space for different tanks while observing normal rules for certification and redundancy. And then the right hand side, obviously with Simon's team, you've heard from earlier today, looking at power profiles for these aircraft in terms of takeoff and climb. And then in the table you can see quite a mix of different architectural component and system possibilities. And I think if you consider the number of aircraft we looked at, you consider this table and a very long list of potential technologies across systems, architectures, materials, operations, and manufacturing, I'm sure you can understand that if we created a matrix of all possible combinations, we would end up with an exponential number of aircraft concepts to look at. So once again, we feel that sort of validates that we have to take a feature-based approach, not an aircraft-based approach, and really focus on key features rather than believing that we could mix and match all of these different options. So in summary, the Scout aircraft, they were developed as a way to evaluate the potential features of aircraft concepts that we felt represented the biggest opportunities and challenges for the integration of zero carbon emission technologies. And the entire team have evaluated these Scouts against a full range of criteria. Yes, obviously the detailed technical assessment with the level of knowledge we've got at the moment of those technologies, but also reflecting on the industrial challenge, the operational challenge, both in terms of airline and airport, but even the aesthetic and inspirational aircraft of impact of these aircraft, because I think there is a big change coming for the flying public as well as our industries, and we need to sort of think about how we reflect on managing that change and make sure people feel comfortable flying. We also developed a whole set of categories of different technology bricks, some of which Simon has mentioned in his presentation, and you can see them listed there and the symbols we use from them. Some are classic, some are quite new to us in aerospace, certainly civil aerospace, with things like cryogenics and hydrogen storage and distribution. And it's also obvious to us that not just the on-aircraft technologies, but there's such a radical change coming with some of these energy systems that the underpinning technologies and materials, lifecycle management, been able to mature a product more quickly in the design phase, and the sustainability topics, as well as all the operations technologies as well, are going to see a massive transition also, and we can't manage that independently. There has to be a synergy in the development of the aircraft solutions and the technologies, even just on an obvious one example being refueling technology as an example. So these are the sort of headlines of technology bricks, and the information and reports we create here will flow up into the main technology roadmap deliverables, which is part of the main objectives we were given by Bayes at the start of the project. In phase 3, and my apologies for the complex slide, we split the team, taking those technology bricks into account, we split the team into a number of different challenges and streams. And to try and explain the difference to you, the challenges relate to specific integrated solution of a technology or an architecture onto a product, and the streams related to capabilities, sometimes individual capabilities of things like mass assessment, through life safety and certification, these examples. So there's sort of a difference between integrated challenge and individual capabilities. And this is where we really started to understand the important features, and took these challenges and stream inputs and started applying them to the scouts in a way which enabled us to understand what those key features were and complete the scoring that I mentioned earlier. I should mention that we've not been on our own in the internal team, and I said earlier we've had some significant cascade of packages to academia and to industry, and that's been a tremendous benefit for us. That's been twofold. That's been covering gaps of capability in our team on things like cryogenics, noise assessment as two key examples, but also as we've begun to understand what we felt were the important areas to investigate, we have been able to develop packages to tap into academia and industry to find capabilities to cover that we don't have ourselves. And this has been a major contribution to the work we're doing, and indeed to the outputs that we have ahead to deliver. So I take this public opportunity to thank all of you on the call who are involved in that. So thank you very much. So what next? Okay, so we've written a lot. We have a mountain of data now, and we have a significantly developed understanding to where we were at the beginning of the year. So now we're trying to refine those concepts, those scouts, down to 3 specific concepts for the regional, narrow body, and the mid-size, but in the context of feature base. So we haven't specifically chosen one of the 27 for each zone. We've looked at the right features and created an aircraft from those features for those 3 concepts. So we're trying to combine as many of the key features as possible. And it's important to note that these concepts remain integration vehicles. We aren't trying to specifically optimize the design. We're not going to spend a long time laying out detailed airframe sizing, because that's a capability which is well known and available. Our job is to look at the key integration points of enabling technologies, particularly around obviously the fuel system and the propulsion system, but also structural and system developments which may have to change. Like, for instance, we may have a completely different power budget on the aircraft. We may no longer have bleed air from a systems point of view, And if you have a wing which doesn't have fuel in it, that opens up a completely different design space in terms of integration of movables, as an example. And through doing that, we expect to feed into a top-level value assessment with the whole aircraft modelling team with David Debney, primarily through bottom-up integration technology bricks, but also with elements of top-down for whole aircraft topics like certification and airport operations. So thank you very much for listening, and I look forward to answering your questions later.
Hello, Tim Goldsworthy.
Hello, Katie.
So thank you very much for that presentation. It was really exciting to see all those Scout aircraft, and many of them look very, very different from one another, and different from things that we expect or see, you know, when we go to our local airport on our holiday to Malaga. You said you were moving now into a phase of defining 3 concepts, and you spoke about regional aircraft, a single aisle and a mid-size. Have you considered application to larger or wide-body aircraft? What's the logic at stopping at that mid-size size?
Yeah, a fair question, Katie. I think when the project was launched, we deliberately bracketed our aircraft scope from regional up to what we probably call extended single aisle in current language. As this covers 90% of the flights that are performed today. And also we felt offered the best opportunity for the integration of genuine zero carbon technologies. I think as many of you on the call will probably be aware that there are activities, other parallel activities looking at sustainable aviation fuels for wide body, long range application. But that's a net zero solution. That wasn't our mission. Our mission was zero emissions. So we chose to focus on that middle bracket of the high volume of flights today. But I'm sure in the future, scalability of our solutions will be a topic. And you mentioned the different shapes. We have explored many shapes, as I showed in that presentation. And we don't need to be radical for radical sense, but clearly the integration of these systems, and particularly the tanks of new fuels, are going to drive, I think, some different architectures to what we've had in the past, and may drive some different top-level architectural solutions of aircraft for sure.
So my role in the project is in industrialization and thinking about the impact on our industrial footprint in the UK. Those architectures that you've spoken about, do you think that they could present a threat or an opportunity for UK supply chain? Like, how might those changes affect Britain and its current supply chain?
Yeah, I think that, well, there's probably 2 parts to answering that question. I think the aerospace business has a long and, I think, proud history of remarkable efficiency improvements on the kerosene fleet. So those capabilities, those technologies, those industries that have done that's as relevant today, maybe even more so going forward for these different fueled zero carbon solutions. So any company based on those around the efficiency, whether that's performance or indeed cost, has got that future, but will have to adapt for the different architectures, maybe different materials, different environments, cryogenic environments, for instance. So there are opportunities to maintain and grow for those businesses. But it would be wrong of us not to say that there is, for some areas, we're at a fork in the road here. You know, we've got some technologies that may no longer be applicable going forward. Fuel system, kerosene-based fuel system equipment is an obvious one. Also, maybe we wouldn't expect to take bleed air off future engines just for, we wouldn't want to give up that efficiency. So we're going to have electrical solutions for whatever bleed air supplies today, primarily de-icing and ECS. I know there are electric non-bleed air solutions for those technologies today, but if we're going to have a virtually all-electric aircraft, we're going to have to consider the power budget at the aircraft level. So we're going to need more efficient electrical solutions for all those different systems as well going forward. So yes, it'd be naive to say there isn't a fork in the road, and I'm sure that some of the companies involved in those areas are well aware of that and already making plans to adapt their business, and if indeed some of them are engaged in our project and doing so.
And do you see any threat to the incumbent UK supply chain? You know, is there a chance that if we move to a specific architecture, it will lend itself better to to supply chains in other places?
No, I don't see that particularly, Katie. I think it's about adaptation. It's about people, individual companies recognizing their current capability and portfolio and how it fits with the way technology will go in the future. I don't think there's that global threat to our existence. No.
Okay, thank you so much, Tim. I'm going to hand over now to our next speaker, who is Naresh Kumar, our head of sustainability, who will talk to us all about the sustainability targets and challenges around achieving zero carbon flight. Thank you so much again, Tim.
Thank you, Katie.
Good afternoon. A lot has happened since the FlyZero webinar in May that many of you may have joined, both within the project and on the government's response to the climate emergency. Let's start with the UK. The government had already set in law to deliver net zero by 2050, and I'll come on to the Climate Change Committee's advice to the government on how to deliver this. An interim target to reduce emissions by 68% by 2030 was set last year. However, earlier this year, the government further strengthened this to deliver 78% emissions reduction by 2035, presenting an even bigger challenge for all sectors. Very significantly, the government's 10-point plan includes jet zero to cover aviation. The UK and Italy are partners in climate change, leading the COP26 process for the United Nations. The G20 Environment Ministers meeting in July agreed very significant proposals to protect the planet, its biodiversity and resources. It also agreed very substantial funding needed to tackle adaptation, to manage the increasing effects of extreme weather and devastation from hurricanes, droughts, floods, and other effects, which I'm sure members of the audience will have seen on the news. These discussions and agreements at a United Nations level are central to tackling the climate emergency. Prevention is always better than cure. So, I'm not surprised that the United Nations has been determined to ask all nations to commit to doing their part and attach urgency to emissions reduction to limit global warming to 1.5 degrees, as was agreed at the Paris Agreement in 2015. Around 70% of the nations have set net zero targets already, and this is up from 30% pre-COVID. There is increasing realization that action needs to extend across all industrial sectors that serve society worldwide. For aviation, which extends beyond international borders, working together will provide a platform for collaboration. Investment in new zero emissions aircraft technology will be key in decarbonizing aviation and thereby tackle the 2 to 3% emissions it is responsible for. In July, the Intergovernmental Panel for Climate Change published its 5-yearly update on the physical science basis. This report once again confirmed the effect global warming is having on the planet, its atmosphere, the oceans, and the continents. The detailed analysis of radiative forcing associated with aviation, as shown on this chart, shows that CO2 remains the main greenhouse gas of concern that must be reduced or eliminated. The non-CO2 emissions also affect radiative forcing, namely the impact of water and oxides of nitrogen. These effects are complex. For water, which can lead to the formation of contrails. These can be influenced by the surrounding conditions within the atmosphere, the so-called ice supersaturated regions. They can be affected by the amount of water that's discharged from aircraft and its form, i.e. whether it's vapor, its droplets, its temperature, as well as particles that may be in the exhaust system and possibly the mixing associated with vortices that might emanate from aircraft. For oxides of nitrogen, so-called NOx, these can interact with other chemicals in the air. For example, NOx can in certain conditions lead to the formation of ozone and in other conditions lead to the reduction of ozone, varying in altitude. NOx can also reduce methane, and methane itself, and this is a good thing, methane itself is about 30 times more potent as a greenhouse gas than CO2 itself. NOx can also reduce water moisture in the atmosphere. So all of these effects can cause some cooling and warming, but the net effect is one of warming. In a number of areas, the level of confidence associated with these effects remains low, so more work needs to be done by the scientific community to improve that certainty. In FlyZero, we are assuming these effects must be mitigated. So as part of developing concepts for zero carbon emissions aircraft, we're also assessing the best way to minimize or eliminate non-CO2 effects, as well as reduce noise. We heard earlier from Simon that hydrogen offers potentially the best prospects for zero carbon emissions aircraft. Last December, the Climate Change Committee published its 6th carbon budget guidance to the government on how to achieve net zero. Within this, they detail a number of key steps. These include take-up of low-carbon solutions, expansion of low-carbon energy supplies, and reducing demand for carbon-intensive activities. And for the first time, aviation emissions have been included in the UK targets. Of all the public transport modes, aviation has the biggest challenge to decarbonize, largely driven by the need for high energy density fuel. Looking at the charts from the Climate Change Committee on this slide, as other sectors decarbonize, aviation, shown in purple, will likely become the main user of kerosene from oil in the 2040 to 50 timeframe. Last month, the government published its hydrogen strategy, joining countries like Germany and France and many others worldwide. It's easy to see how fast-changing the energy landscape is. The chart below shows the dramatic ramp-up anticipated for the use of hydrogen in the UK. However, this may fall short of what might be needed for aviation. Whilst acknowledging that hydrogen will be critical for UK's transition to net zero, the current strategy may not stretch quickly enough to support the needs for all the different sectors, including aviation. So in conclusion, the government's 10-point plan to reach net zero includes delivering zero carbon emissions aircraft by the end of this decade as part of Jet Zero. There is no doubt in my mind that emissions reductions from aviation will be an important contributor to achieving UK's target for net zero and thereby help to limit dangerous climate change and to protect the planet. Thank you.
Thank Thank you so much for that, Naresh. Your passion on sustainability really comes across very clearly in the presentation. So thanks for holding on to answer a few questions. Before we do that, I'd just like to say after this Q&A, we're going to hear from Mark Howard, and then we'll have a Q&A with all of the speakers today. So if people want to put questions into the Slido, then they can do. I know there's a QR code on the screen just now, or there's a code in the meeting invite. And I'll read out the code just in case you can't find it. The meeting invite might have gone to your spam. So the code is 902188. That's 902188. So get your questions coming in, and we'll have a Q&A with all the speakers in a bit. So Naresh, turning to you, you were talking about aviation and said that it accounts for 2 to 3% of global emissions. When you take into account non-CO2 effects, is that figure not larger?
Yes, it is. It could be twice as much. As I explained in my brief, the impact of water and NOx emissions will also add to the overall climate impact. Reducing tailpipe emissions from aircraft will address the lion's share of effects, but the use of hydrogen as a fuel, a zero carbon fuel, will generate around 3 times the amount of water emissions compared to kerosene. So there's a higher chance of producing more contrails in ice supersaturated regions of the atmosphere. It's worth noting, however, that contrails from water emissions have different characteristics than those that might be produced from particulate matter from aircraft that burn kerosene from the exhaust in terms of optical density as well as persistent. But these are areas that we are investigating in detail with the help of key universities in the UK as well as industry, so that we can actually understand both the effect and, more importantly, how to mitigate and avoid the impact of these non-CO2 effects.
So you're saying that both types of aircraft, kerosene burning and hydrogen burning, could create contrails, which are the clouds that you see in the sky, but it's possible that the hydrogen aircraft might be a bit less damaging depending on how persistent those contrails are. Is that right? I've understood.
Well, the contrails will be different by nature. So at the moment, we don't know whether they will be less impactful on global warming or radiative forcing or more. But at the moment, initial indications are telling us that the effect is likely to be about the same.
Okay, thank you. So tailpipe emissions are the things that come out the back of an aircraft, say a jet engine, or even in older aircraft, internal combustion engines, and directly pollute the sky. But of course, it takes energy to create the aeroplane in the first place. So if we think more about circular economy and sustainability through the whole life cycle, is there more that aviation needs to do in that regard?
Absolutely. I mean, circular economy. So being able to reuse and recycle materials in every walk of life will enable us to preserve the limited resources we have on our planet, for sure. The aviation industry already recycles well over 85% of materials it uses. And this makes sense, particularly important, for example, applications where rare materials used, for example, in superalloys that I'm familiar with, for high performance applications like jet engines are really, really important to preserve. These are processes already in place that recover such materials to reuse within the sector. In Rolls-Royce, they call this process revert for obvious reasons. The development of zero carbon technologies will likely put us in a different landscape where different materials are going to have to be used. I'm thinking of things like, obviously, batteries, different types of motors, lightweight materials, such as carbon fiber composites, etc. So it's really important that we extend the best practice of today to these new materials, and more importantly, to new processes that will be innovated as we go forward. I can tell you that we're looking in detail at these aspects, including decommissioning of aircraft as well as end-of-life considerations.
That's really interesting, Naresh. And then the last question. COP26 is bearing down on us rapidly. It's going to be at the end of October, beginning of November in Glasgow. What are your hopes for what will be achieved at COP26?
Well, I'd love to be a fly on the wall with the Prime Minister's team. I think this is a huge opportunity for the UK to demonstrate its leadership and set an example for the rest of the world on how to tackle the climate emergency. I really hope that the Prime Minister's team is able to convince even more nations to commit to addressing global warming with the urgency that it really deserves. I personally am particularly looking forward to the United Nations recognizing the significant role that zero carbon technology can play in developing solutions to reducing emissions from aviation. And the sooner we implement projects like FlyZero so that we can develop the technologies, the sooner we can deliver the much needed emissions reductions.
Excellent. Thank you, Naresh. So we're now going to pass over to our Head of Commercial Strategy, Mark Howard, who's going to be talking about some of the work that his team has been doing.
Good afternoon. My name is Mark Howard and I head up commercial strategy for the FlyZero project. Today I'd like to take you through the case for targeting zero carbon aircraft, our rationale why we think it's the right thing to do. I would like to provide you with a different perspective on why sustainable zero carbon flying is important, not only for aerospace and aviation in general, but also to the public and to the wider economy. I'd like to introduce you to our onion model, and of course at the core of the onion is aerospace, this high value, high technology sector, which already brings high value jobs to the economy and an awful lot of exports. In the second layer, we have aviation, the key enabler for connectivity. Flights and passenger numbers lead to fixed airport infrastructure, significant investment around ground services, lots of jobs around the airlines, and ultimately significant investments around research and development on the topic of ground infrastructure. To reflect on this connectivity, I'd like to share with you this chart from the ICCT, admittedly from 2018. However, it does show the dominance of the US in terms of air transport. However, UK is there in third place, clearly dominated by international travel for the UK. It's a complete reflection of our island nation status. Moving out a layer on the onion to layer 3. Clearly, the demand for aviation leads to a need for fuel and energy infrastructure, which I guess ultimately becomes the fundamental enabler of the whole system. But it's really important to understand that as we transition to new fuels, new zero carbon fuels, all that infrastructure needs to be put in place to enable that to happen. That obviously will not only lead to a greater demand of what we believe will be more hydrogen, but it will lead to more jobs in hydrogen production, of the transportation, the storage of that, and of course, we've got increased markets for things like hydrolyzers, where the UK has some key expertise. And of course, Changes of fuel drive demand for new equipment, infrastructure, and all of the energy to run it. So what does all this bring? The aerospace, aviation, energy. It brings us connectivity. It brings us the ability to travel as tourists, to trade, to enable supply chains, to make sure we have inward, outward investment. And ultimately it has productivity effects, which impacts the economy overall. It has great economic impact. Connectivity is a key enabler of our island economy. But we can't do this at any cost. We've got to look after our environment. We've got to mitigate any harms, any emissions, any impacts that we have. But if we want to stay connected, it's really important for us to act, and act towards looking after our zero carbon future. We can look at the model from both the inside out and make all of the arguments that we've just talked through. But we can also look at it from the outside in and recognise that there's a whole load of synergies that we get from being connected. That we do want to have that good environment. We do want to stay connected and go on holiday and have delivered this global Britain objective, and recognise that flying has really strong societal benefits. The fact that it is one of the major ways that the UK stays connected, recognising that 95% of the flights taking off from the UK are international. Those benefits, those societal benefits, come from economic, trade, business connectivity, the family holidays, the tourism, and actually, if we looked to restrict aviation, it will not come for free. It would not come without an economic impact because of the way in which where we're placed in the world. The bottom line that we would like to make, the point I'd like to make here, is that restricting aviation is absolutely not free decarbonisation. So I'd like to turn to traffic forecasts. And they're clearly, some updates are starting to come through now. We've seen Boeing up issue their global market forecast in the last few days. And their indications are something of the order of post-pandemic. This is 4% passenger traffic increases year on year, just over 3% aircraft sales increases. And that is clearly the view of demand increasing, and from a volume perspective, what is obvious is that the single aisle narrow body market will remain dominant, and that Asia will be the market with the most growth. As FlyZero, we're developing our own market model. We're looking to make a market penetration forecast to test the competitiveness of the FlyZero archetype concepts. With this, we can then make an assessment of the sustainability impact that a zero carbon aircraft could have. Of course, ultimately, this is super dependent upon when an OEM is ready to launch such an aircraft. And from a sustainability perspective, what we need to do is for that OEM to act sooner than maybe they might plan to do. And because that will probably have a much more significant impact on the contribution of zero carbon aircraft on the 2050 net zero target. So our exam question might be, how do we help, how do we support an OEM to act sooner, to act quicker? And the key issue is about having that technology ready, making sure the key technologies that the UK are able to deliver is ready on time, actually ahead of time, to make sure that early delivery can be made. So looking at fleet trends, this is all pretty much pre-pandemic now, but we don't really anticipate things changing dramatically post-pandemic. It's clear that as demand increases for flight, the size of the aircraft and its range is also increasing. And along with the move to more efficient aircraft as older airframes are retired. Now, it's pretty clear that the narrow body aircraft is really dominant here, and it's the larger aircraft that have the more significant growth. What is equally important is the retirement of an ageing fleet. There is a view that the airlines can only afford a single fleet refresh between now and 2050. Given that 90% of the global fleet at the end of the 2030s are aircraft not yet built, then an early launch of a zero carbon aircraft becomes super important to make sure we capture the maximum CO2 reduction benefits. It's pretty clear that the FlyZero zero carbon archetype aircraft, the addressable market, really obviously lies in that narrow body sector. It's fair to say regional markets clearly an opportunity, but they are relatively small and certainly less impactful from a CO2 perspective. So if we want to actually attack CO2 emissions, then we've got to go for really get to the narrow body sector and above. We cannot shy away from the infrastructure challenges. They are certainly not insignificant. To that end, we've engaged with a number of airports to address the core question of, could liquid hydrogen be a feasible energy source on an aircraft? Can we get it there? Can we get it onto the airport and into the aircraft? And ultimately, we're trying to address those big questions and understand what the big challenges are. It's not about solving the problem once and for all. It's really trying to understand what the challenges are and the fundamental feasibility. To that end, we've engaged with partners Arup and Jacobs to look at the end-to-end supply, basically from generation through to the airport boundary, and also then look at quickly on the distribution on the airport itself. And I have to say, I'd like to take this opportunity to thank the airports for their engagement so far. Your help has been really appreciated and really supportive, and we look forward to carrying on that work through the next quarter of the year, and look forward to sharing some of the outputs with you as they come to fruition. As part of our studies, we've been taking a look at the fuel demands that will be required should we have good adoption of a zero carbon aircraft or a fleet of zero carbon aircraft. And essentially, I'll just reinforce that point. These charts are optimistic towards the market penetration of zero carbon aircraft, and it was ultimately done to make sure that when we pass these demands on to our partners Jacob and Arup, that they understood the potential stretch target that we might need to strive for at some point in the future. So this chart shows currently just the pure conventional kerosene stroke SAF view of the world. And this demand is clearly not insignificant and growing from 13 billion litres today in the UK to 25 billion by 2050. So actually the introduction of zero carbon aircraft doesn't make the need for kerosene or SAF go away. There is clearly an opportunity to burn less CO2 generating fuels, which is actually quite striking from this chart. And that actually helps SAF because it reduced the demands on SAF volumes. But again, just to reinforce, the scenario assumes quite significant market penetration of a zero carbon aircraft. Now introducing the volume of liquid hydrogen onto the chart for equivalent flights. That's nearly 25 billion litres of liquid hydrogen required by 2050. 25 billion litres of a fuel that generates water at the exhaust, but 25 billion litres that needs to be transported to the airport onto the aircraft. But what do we need to do operationally to make this work and be effective? We need to consider the end-to-end cycle of the aircraft operation to ensure that the airline, the airport and the airspace work seamlessly together, and that the aircraft does its part in supporting this collaboration. So I'm going to focus on two elements of this: the aircraft turnaround and the airspace challenges and opportunities that we have in front of us. So the first question might be about turnaround times. Why are they important? Well, actually, they affect the airlines and the ground handlers, time spent on the ground, affects the airport capacity consequently, and ultimately the airspace capacity. An aircraft turnaround could be viewed as a Formula One stop, looking for maximum efficiency with ultimate safety in mind. The graphic on the left shows all of the elements that we're looking at in terms of addressing the process. The refueling, we're looking at things like linked to the aircraft architecture. How many hoses do we need to actually connect to the aircraft to get them refilled? We're looking at things like safety zones, keep out zones, and obviously looking then to understand how far we might need to challenge current regulations to make sure that we achieve our ultimate aim of maintaining current turnaround times in a safe way whilst enabling other operations happen in parallel. And to that end, we've got partners Costains and the Health and Safety Executive supporting us to actually address some of the elements of this big exam question. The biggest game changers for future aviation are likely to be in the form of electric and hydrogen powered aircraft. However, this doesn't mean the drive for further efficiency will not be essential for further gains. New fuels will still be a significant cost for airlines, which means the strive for improvements in aircraft design will remain. At the same time, the air traffic management systems will have their role to play, exemplified by the figures on this chart, which show the challenges that we face today. If an aircraft arrives at an airport just stacked in a holding loop for a prolonged time, then I'd like to say that actually that isn't sustainable flying. And I guess equally, if an aircraft flies a non-optimal flight route, then maybe that isn't sustainable flying either. And actually, whatever fuel, be that Jet A1 or liquid hydrogen, if we burn more than necessary, then that isn't sustainable flying. And by managing delays and enabling airspace, airport capacity, the domain of the air navigation services providers can support the airlines and the airports and act as an enabler for reduction of emissions, including CO2 and noise. So organisations such as ICAO and Eurocontrol drafted long-term plans listing various ways for improving the current situation. Each airport and piece of airspace has its specific constraints and potential. So it's not a one-size-fits-all solution. However, the most efficient flight paths, allowing the most efficient air traffic flow, reducing delays, can be achieved by a method called trajectory-based operations, which is underpinned by continuous descent and climb operations. These can be implemented at every airport to a certain degree, and they don't require additional onboard equipment. What is more, the modern aircraft are equipped well enough to execute trajectory-based operations already. The core goal here is to achieve a system that allows no conflicts, where planning and management of flight is highly reliable and receives good support from automation and artificial intelligence technologies. And finally, where the capacity is increased, thanks to a well-planned, well-managed and executed service. I guess the key point here is that if we're going to achieve our carbon reduction goals, we've got to look at a game of marginal gains, just like the British cycling team. So just to wrap this up, it's pretty clear that the benefits of aerospace are beyond just aerospace alone. We're an island nation, we need to stay connected. The traffic forecasts, again, the growth is looking like it's remaining. It will continue to grow post-pandemic. And whilst we want to all see that growth, I think we all probably want to do it in a more guilt-free way now. And our proposition is that liquid hydrogen is the route to that. In order to actually deliver that liquid hydrogen to an aircraft, of course, the infrastructure is critical here. Kerosene is well established today. We need to make sure we address the feasibility and the challenges associated with getting this new fuel to the airport and on board the aircraft. And quite clearly, from a market penetration, from a mitigation of CO2, the aircraft needs to be super competitive. And finally, I guess we need to look at the overall aircraft operation in very much a system of systems way, making sure we can support both the capacity of the airports and the airspace to deliver our ambitions around a growing fleet. So thank you for listening, and I look forward to taking your questions shortly.
Hello, Mark Howard. Thank you very much for that presentation. The breadth of what you and your team have been working on is really, really quite impressive, all the way through from energy infrastructure to onion models for economic cases. I think it's the first time I've heard onion and aerospace together in the same sentence. So that will stick with me, I think, for my whole career. So really interesting. Coming right to the crux of it, though, aviation has the sector's got a bit of an image problem, which is perhaps not entirely fair. This is my view. I'm in sector, though, given that the clothes that we wear are a bigger polluter and so much harder to decarbonise. But we still have a moral imperative, don't we, to address the decarbonisation issue. Do you think that these technologies are a route to really decarbonising and tackling that image problem and gaining public acceptance of flight over the longer term?
I think, Katie, it's probably fair to say it's a very good question, and I share your views as well. Inevitably, we're taking a good step towards addressing it. I think FlyZero as a project is a good step, and a visible image of the industry coming together and trying to make sure it responds appropriately. And inevitably, we're bringing together a bunch of the core partners in FlyZero. We're bringing together also a bunch of external people to have that same view that we need to go address and invest in these technologies as you describe. I guess ultimately what FlyZero is about understanding what those core questions are and trying to identify what the priorities are in terms of which technologies to focus on to make sure we have the biggest impact. To make sure we actually sort of understand which things we need to actually sort of invest in going forwards. And I guess ultimately, we're looking to shape, the outcome will look to shape the UK response to aviation and where it fits into our global world we sit in. At the end of the day, it's a bit of a baby step we're taking, yeah? It's a bit of an understanding step we're taking, but the hard work will come next. The hard work will follow on, and we need to have some very serious, tangible actions, some very serious, tangible investments to make as we go forward post FlyZero.
So we heard a lot about. Yes, yeah. So the urgency is very apparent from a lot of the different messages from the presentations today. Tim and Simon were both talking about the kind of on-aircraft challenge. You spoke about the energy and the airport infrastructure challenges, and one of the figures you spoke about was 25 billion litres of hydrogen. Can you put that in perspective? And how much might that be for an airport? What are the airports and airlines and energy providers saying about it? Is that surmountable?
I mean, the volumes are huge, yeah? Almost effectively double what we have today in terms of litres of liquid. And to give you a sense of scale, the kind of upload that Heathrow had in 2019 was around about 21 million litres per day. of kerosene. So that's enormous amounts of fuel. And I think in some ways the volumes speak for themselves. I guess the challenge can't be underestimated or even understated. And it's a bit of we're at the start of this journey of getting the right infrastructure in place, both at the airport and also with the energy providers. And I guess the problem is it's a bit of a chicken and egg situation. And which comes first, the aeroplane or the infrastructure or the energy? And I guess ultimately we've got a big coordination challenge. We've got to make sure that they all come together. I guess the beauty we have is that many sectors are interested in hydrogen today, and that's evident from the government's own hydrogen strategy. So I think that's a positive. You might argue that the hydrogen strategy might be good to see a bit more aviation in the hydrogen strategy going forwards. And I guess our message is that the UK needs to prepare for that. And I think actually maybe one message might be that aviation is really difficult to decarbonise, and maybe hydrogen might need to be a priority for aviation.
And last question, because in a minute or so we're going to bring in the rest of the FlyZero leadership team so that they can answer some of the questions that people have been putting on Slido. But you're the head of commercial strategy, so as we move to hydrogen, the fuel takes up more volume, and that volume might impinge upon the space that's available in the cabin. A key question must be, can these aircraft be produced and be commercially viable? So can you get enough people on them? What's your view? Have you looked at that within the project, and will they be commercially viable?
Obviously, that's a very sort of close relationship between the commercial team and the engineering team, is making sure we do have a product which is which will have the right kind of market penetration. I guess initial findings, our early indicators are really quite are encouraging. We're forecasting that we can get to a competitive product. I think it's probably worth saying and adding that actually there are some significant hurdles to overcome. And that we've got to make sure that we can address those engineering challenges. But I think hopefully FlyZero can bring those outputs, outputs set out the pathway for where we need to go, and hopefully get to the right answer, which is a hydrogen powered aircraft in the future.
Okay, amazing. Thank you, Mark. So now, if possible, we're going to bring in the rest of FlyZero's leadership team. So bring back Naresh and hello, there they are. So Naresh Kumar, Tim Goldsworthy and Chris Gear. And we're going to turn to the Slido where people have been putting in questions. There are quite a few. I'm not sure if we'll get through them all, but we've got about 25 minutes to go through them. So let's see how we get on. I'll try and group them when I'm asking them. So apologies to the audience if I bounce about a bit, but just so that we can have a conversation on a topic and then come back. And I wanted to start with some questions which were really about the clarification of FlyZero's mission and how it interacts with the wider community. So there's a question there which says, is the ultimate plan to build an aircraft in the UK for FlyZero, I'm assuming, or is it to ensure that UK gains work share on a new multinational aircraft? So Chris Gear, could you respond to that?
Yeah, thanks, Katie, and thanks for whoever's asked the question. FlyZero was originally set up by the government BAYS, supported by or led by the ATI. And our mission was around zero carbon emission vehicles and to determine what those might look like and actually to address the market, which is the commercial aircraft market. So we're not looking at small vehicles, we're looking at commercial vehicles, carrying 100 people or more with significant range. And our objective is to try and solve the problem, because this isn't a simple answer or problem, should we say. How do we produce an aircraft that can fly and produce zero carbon emissions? And as I can see from some of the answers, there's some issues around, how do we refuel with liquid hydrogen? So our whole objective is to focus on the bits that make up an aircraft. So you have a load of technology bricks, depending on what your solution is, what your fuel solution is, that would change the aircraft structure. You need to develop those to a maturity level say by 2025, so that we can show that we have capability and skills in the UK to support whatever multinational OEM is looking at in terms of an aircraft. I think we'd all like to say, yeah, the UK could build an aircraft and fly it, but the reality is this is a global market, aviation. We need to work within the global community. So what we need to do is use our strengths, which is around some of the systems and integration of these things, and actually then support the multinational companies to build aircraft. And our vision is to actually get something to fly before the end of the decade.
Thank you. And then a slightly related question, from Jenny Body. So can you explain how FlyZero, JetZero Future Flight, which is a UKRI Industrial Strategy Challenge funded programme, and sustainable aviation work together? What's the interaction there in achieving the mission that you just described?
I mean, the obvious answer is we are working closely together with all of those groups, but actually FlyZero, part of the ATI is actually on the JetZero Council. Gary looks after the zero carbon emission side of it, and actually that's where FlyZero sits. So what we're doing and working on is supporting Emma in the JetZero Council. And on the other side of that is the net zero carbon group, and they're looking at what we can do around sustainability. And as well as that, we are talking quite a lot with the Future Flight organization, because some of the things they're looking at are affecting our views on how do you integrate such a structure into an airport. So I'm really pleased to say, Jenny, that we are working very closely with those organizations and are having regular discussions with them at all levels. And we have actually engaged not only BAYS, who are our sort of stakeholder, but we've also engaged DFT. So we're working closely with those two government bodies, as well as we're working with academia and our industrial contribution companies. So I'm sure we're not perfect, but we're certainly out there trying to make sure that everyone is joined up and we're focused on one objective.
Yeah, and that sense of integration and joint mission across people looking at zero carbon, but those also looking at sustainable aviation fuel, I think that's really exciting. At a phase where we don't know how it's all going to pan out, so we need to be taking a more integrated approach. But building on that, there's quite a lot of questions here about sustainable aviation fuels. So we've got one that says, shouldn't sustainable aviation fuels be just as carbon neutral as green hydrogen? We've got another saying, why is SAF being overlooked, from Andy Leather. So Naresh, can I turn to you to start on those questions? Like what?
Of course. Thank you, Katie, and thanks for the folks that have asked the questions. So let me start by saying that sustainable aviation fuels do have a very important role to play, particularly in the short to medium term. These fuels are going to be really important, particularly for the long haul aircraft fleet that operates today. I guess one or two of the audience members might be intrigued as to some of the traffic light system that we've used to assess the different fuels. And I'd just like to clarify, looking at all of the alternative fuels as we did, that Simon very comprehensively briefed, included quite a number of different criteria, not just the potential to reduce CO2. It also included the capacity and scalability associated with the fuels, the infrastructure aspects associated with bringing the fuel to the airport and then onto the aircraft. It included the cost of the fuel, not just today, but what it's likely to be when we get to the sort of middle of the century. So there was a huge number of criteria that we used. And I must admit, when you look at the fact that in 2019, the volume of sustainable aviation fuel that was available to the market amounted to about 1%, well, less than 1% of the total need by the global sector. it is still needing a lot of effort and support in order to increase the volumes. One of the pathways to actually produce SAF by volume is e-fuels or power to liquid. That process itself starts off by producing hydrogen and then further processing in order to create liquid fuel by the use of things like Fischer-Tropsch process, which requires more processing and more energy. So it was quite important for us to understand all of that before we came to the conclusion that actually hydrogen does indeed offer a very high prospect of achieving zero carbon aviation as we go forward.
Thank you, Naresh. And Mark, do you have anything to add on that subject matter of sustainable aviation fuel?
Not massively, apart from just to reinforce Naresh's point about the cost of synthetic for e-fuel for PTL, because ultimately, I think the forecasts are that typically they're around about sort of something of the order of sort of 40% higher than liquid hydrogen ultimately as you forecast forwards. So that becomes quite a challenge in terms of making it a competitive sort of fuel ultimately.
Thank you. Thanks very much. Right, there's a lot of engineering questions on the list, and I am an engineer, so I'm just embark on a little mini geek off here. There's a question there about boil off. I'm just trying to find it. It's to do with the fact that if you've got liquid hydrogen fuel, there's continuous boil off during the operation. And how will that be handled during flight? Does it mean that water vapor hydrogen vapor will be continuously emitted during flight? So Tim Goldsworthy, do you think you could comment on that for us?
Sure. It's I guess it wouldn't be a secret to anyone that the storage of liquid hydrogen, a tank to accommodate it, and the systems which maintain it is a huge focus of our program. And yes, sure, boil off is a known issue and risk, and we know that we would have to store that hydrogen at minus 253 degrees C to keep it as a liquid. In any small temperature rise above that will start that boil off process, and that's throughout the range of the aircraft's operation, whether it's at altitude at minus 55 or on the ground in the Middle East at plus 55. So yeah, that is a massive challenge, but we're well aware of what the range. We've had a significant piece of study in terms of what the range of temperature variation we want to have in the tank and maintain an acceptable, available, usable fuel, and a boil off, which means you have an acceptable pressure or venting. So we still have operational aircraft. So we've worked hard to understand the criteria and the envelope we're working within for the tank, but a lot to do. You're still on the technology solution. I wouldn't say that we've found all the answers this year. We've got lots of questions still to go forward and answer in the future, not just in operation, but also during refueling, obviously, as well, because there are potential losses and boil off and venting and safety requirements in all phases of use of fuel, as indeed there is for kerosene. And we've got decades and decades of experience of handling kerosene, and we're at the start of that journey with hydrogen.
Can I just add that? Sorry, Katie. I was just going to add that some of the things we're thinking about is we need to collect all the open questions that we may not be able to solve in the timescale, because our project is very short if you think about it. So what we will make sure is we've captured any open questions we can't solve, but our initial findings, we are looking at that question in particular. Sorry, Katie.
No, I was going to say that refueling point is really interesting, and perhaps we could come back to a bit of a discussion on airport infrastructures, because there's some questions linked to that. But before we move off the technical stuff, there's some questions about battery. So is FlyZero considering battery? And what range capability could that have compared to hydrogen fuel cell? There's another question about hybrids as well, and whether we're looking at hybrid aircrafts. And there's a lot of different fuel sources, isn't there, that we could consider in the mix that then might impact onto the infrastructure question as well. So Chris, do you want to start, and then Tim, you could maybe add in.
Just to say, we're just about to publish our first report, which is actually going to be on primary fuels. And we do consider batteries, hydrogen, gaseous and liquid ammonia as those that give us zero carbon. So you will be able to shortly see that in the public domain, and that will describe it better. But obviously, because we're looking at longer ranges, and batteries are only very good for short range vehicles and small ones, they don't sort of come to the forefront of something we would see accessible today based on the technology we can see today, and also the technology we think might be available in, say, 5 to 10 years' time. That's not to say batteries won't have a role to play, and we are clearly looking at hybrid type vehicles, which might comprise of batteries with fuel cells with some form of hydrogen. And that, again, is some of the initial work that we're still working on. So we don't have all the answers today, but we certainly recognize it's something to continue to think about. But as our primary energy source, a battery won't actually support what we're looking at.
Yeah, I think that's a very good summary, Chris. Thank you. I think, yes, it comes back to the range of aircraft and vehicles we're looking at again. I would just point out that when we made that decision on the battery and the summary that's in that primary fuel paper, we didn't do that on our own. We dealt with the academic and business institutions, the experts of that we could get access to, and we asked not just state of the art, but what is their projected development. And even with that projection, the most optimistic view of projection, we still didn't get a battery performance which supported the sort of bottom end of the range size of aircraft we were looking at. But there is that option with hybrid matched with other technologies, other fuels, that we could get the boost we need for takeoff and climb, and then have efficient zero carbon other fuel systems take over and get a balance between a battery solution and an alternative fuel solution. That's definitely in scope.
And just to be clear, the bottom range that you're assessing in FlyZero is still quite large, isn't it? It's like a regional that seats maybe 70 people. So batteries potential for VTOL, for sub-regional is obviously much higher.
Yes, indeed. Yes, and I guess people interested in the industry will see there's a number of companies all over the world looking at that sub-regional battery solution as well, but out of our scope as defined in our grant offer letter.
So will you assess hybrids, either kerosene electric hybrids or kerosene hydrogen or hydrogen electric? Will you assess those this year?
I think the focus for this year has certainly not been kerosene hybrids. I think it's more the hydrogen battery, it's more the zero carbon solutions that we have looked at. And that's a new question to me. I'd have to take counsel with the rest of the team, but I don't even think going forward we would look at the kerosene options, because once again, it's not been our ambition and our scope. It may well it could get added. We could add to our scope with that, but it's not what we've done so far.
It's a really good point, Tim. I mean, our scope is on zero carbon emission, and that's what we're focused on, and that's the question that we've been asked by the government to answer. So clearly, that's what we're trying to do. There are lots of people also looking at net zero, as I mentioned, within the Jet Zero Council. So we're supporting them, and we can see there are stepping stones between net and zero, but our mission is to look at the zero.
And one of the questions says, well, through these zero carbon solutions, you might be able to address, say, 90% of aircraft. I will try and find the name of who put it up in a minute, but there's still 10% of aircraft potentially remaining on kerosene or on drop-ins like sustainable aviation fuels. What does that mean then for the airport infrastructure and for the fuel mix and how we deal with that? Mark, could you come in on this one?
Yeah, sure, Katie. I guess inevitably that kind of ambition will be a very much long-term ambition. Yeah, that's in the 2060s, 2070s before you could even get to that kind of mix. Inevitably, the view of if you can get that kind of penetration of a hydrogen aircraft, that will be really sort of getting into the full coverage of the narrow body, and even then getting into a medium range type product if that can be proven to be feasible. So I guess from an infrastructure perspective, the challenge, of course, is managing a transition. And that transition challenge from now to a fully fully hydrogen-powered fleet is a significant challenge. So, in every our desire is to understand what those questions are, try and forecast what those solutions could be. We haven't necessarily got all the answers yet. We're 8 months into a project, so it's the kind of questions we're looking at, but we haven't got full answers yet, Katie.
Do you have a feel if there's a gap between, and this is another question on the list, I'll read it out. So how much more ambitious do the UK or global hydrogen production targets need to be in order to ensure that demand is met for the aviation sector?
I mean, the honest answer, very much more ambitious. And I think the rationale for saying that is that actually those ambitions haven't really been properly articulated yet for the entire sector. We had Airbus announce their Zero E program a year ago, had the summit over the last couple of days, and I think the world is waking up to the exam question, but has everybody really got hold of it yet? I think the answer is no. I mean, nobody's really put out a full sort of global market forecast yet with the kind of content of the numbers of hydrogen-powered aircraft that you might anticipate. So the exam question really hasn't been set. As I said to you earlier, it's a bit of a chicken and egg situation. What's the aeroplanes going to look like? What kind of market penetration can we anticipate? We think it's probably going to be very high, which will be a transition challenge. But until we've actually articulated that to the rest of the world, I think it's still a very wide and open exam question.
I think I can add, it's fair to say that government's supporting a green hydrogen facility in Teesside through the DFT, but we can see that capacity's probably already been allocated to various transport industries, but not really allocated to aviation. So there will be a challenge at some stage once we get down this route to work out what our vehicle might do and what its fuel requirements might be, about how we can meet that.
Yes, I travelled on my first hydrogen bus in Aberdeen the other week, so it's my first hydrogen travel. So yeah, it's not for a single mobility sector, but how will the mix pan out? Chris, there's a question here which is I've lost it. It was about the United States. So, like France and Germany, they're going after hydrogen. The UK is looking at both hydrogen and sustainable aviation fuel. But the US is really laser beamed in, as far as we can tell, on sustainable aviation fuels. And the question was, should we be trying, or can we influence the United States to also look at liquid hydrogen for aircraft?
I think, like all these things, the SAF will give some benefits in terms of the amount of carbon it will put into the atmosphere, which will be less than kerosene. So there is a benefit to it. But there is also this massive infrastructure that the Americans will have to produce if they want to use SAF as the way forward. And I know they've already launched some programs where they're going to commit to, I think it's $4 billion to create some infrastructure to make SAF. But that won't cover all the aviation industry. And I think it's up to us to push the actual reason we're doing this is we want to reduce the amount of carbon in the atmosphere, and we want to support the environment and society, and that means you still have to go and do liquid hydrogen as well. It's not a one or the other. You need to do both, and I think that's a key message that we've learned while we've been doing this project, and it's a key message for the aviation industry. We need to do both. So how do we do it? And it's a problem. It's a challenge. It's a colossal cost. But it's important. So that's how we've got to think about it.
Okay, and then maybe two more questions. So there's a question here from Doug Greenwell. He says, lots of unconventional configurations shown, but does the UK have the aerodynamics research and ground test infrastructure to develop one of these concepts? So, Tim, could you maybe respond? And then, Chris, if you could come in and talk about FlyZero follow on and how we might take it forward. That might be a really good place to end.
Yeah, thank you, Katie. Yeah, as I said in response to an earlier question from you, that we do have a number of adequate architectures, and I guess if I go back to the start of my career, when you're at Heathrow, you look for the fence, you would see lots of different architectures. You see 2 engines, 3 engines, 4 engines, all on the wing, all at the back, and for some of the 3 engines, a mixture of both. And we've gradually converged on twin tubing wings. So when you look for defence now at Heathrow, you have to be in the business to recognise the difference between products. We've been just squeezing a few percent out of that optimum shape. We're back to the beginning now. We don't actually know what that radical architecture, what the optimal architecture solution is, and we will see lots of different solutions. The storage of the fuel in the wing is much more problematic because of the need for a pressurized tank if it's liquid hydrogen. So an optimum configuration to house that may not necessarily be tubing wings. So that's why you see such a breadth of shapes, and certainly from historical reference, they look very unusual, some of them. But that may well be the optimum. It may well be the design space we have to go into. And we've done that as I think I emphasized in my presentation, but not to sort of come up with that top-down aircraft solution, but to come up with the integration challenges that these technologies will give the aircraft, and then come back the other way. How will we adapt the aircraft to cope with those integration challenges? Because in this first year of this work, that was the only way we could approach it. We didn't think we could start the aircraft and then try and believing we could solve it aircraft level and stuff all the bits into it. That wasn't the approach we should take. For sure, when we got those radical architectures, if we do end up with something that is very different and we have to start afresh our understanding of the tools and the capabilities to analyze it, then yes, that is a big capability topic to be addressed for sure. I wouldn't deny that.
Okay,
Chris,
can I just add then? Yeah, sorry, Katie. So really, part of what FlyZero is doing is creating some capability and skills in the people, which we have some fantastic people working on FlyZero from around the industries within the UK. So they're seconded, and some of them are fixed-term contractors, but they are developing capability and skills around how do you model some of these issues about whole aircraft design and that. So I would like to see some of that retained for the future so that we can build a capability in the UK. And clearly things around aerodynamics and those specialist skills we need to maintain to a level within the UK to help us in the future, and also get us in that position that we can globally compete and support, the global aviation organization. So I'm really keen that we do that. So we're hoping, and what we're pushing the government for is to let us carry on with FlyZero in some other format maybe, but carrying on with what we're doing and hopefully helping the aviation community develop some of the, I'll call them technology bricks that we see are necessary for zero carbon emission. And what we'd like to see is try and link that back into, ground testing of those technology bricks and integrating them into a system technology brick. And getting industry involved to help us do that. And clearly, my vision would be, I want to see those fly in an aircraft, because like anyone in aviation, getting something into the air is fantastic. And actually, there's a step change in the approach you need to get it in the air, which is a lot more complex than running it on the ground. And that's where all the value and all the necessary knowledge needs to be to help us do that. So I'm extremely keen that we try and keep going with this.
Brilliant, thank you. That's a great place, I think, to draw the Q&A to a close. So thank you to the audience who've asked absolutely loads of great questions. And if we've not responded here, I'm sorry, there were too many to get through. But please approach us, and we'll try and respond. There's an email on our website, and we're just trying to engage with as many people as possible, because more than us and the work that we're doing, this is a mission for the UK and the globe. So I'm sure some of the people on the phone can have a big impact on it too. We'll bow out now and hand back to Chris for closing remarks for the event.
Thank you, Katie, and thank you to the other leadership members for running this afternoon. I hope you, the audience, have enjoyed it. We really do appreciate your questions, and apologise we can't answer them all. But it's great to see the interest that we have out there. And as we discussed this afternoon, there's some really significant challenges to overcome to deliver a zero carbon emission flight aircraft. There's some huge market opportunities, but also some colossal infrastructure and funding issues that need to be overcome. So there is a lot to do here. And so what we're really talking about now is not the way aircraft would have been in the past, where we're evolving the platforms to meet the requirements. We're talking about massive disruption to what you see, how we operate today. And that's going to be, like anything, difficult to implement. But we need to act now to protect our planet for future generations. And, confidence is increasing that technology has the potential to address the carbon challenge. We can innovate our way to sustainable global aviation growth, but it needs us all as a global aviation community to do it. We can't do it as a separate state. And I think that's really important to recognize that. So, to support the technology and innovation in industry that will deliver on zero carbon emission aircraft, the Aerospace Technology Institute is seeking that further investment as part of the government's comprehensive spending review. We hope you will support us in trying to do that. We can see the benefits of what we're doing, and we think it's very valuable for the UK because we're building the skills and capability that will help put us into a global position to support the global OEMs. In doing so, the aerospace sector can boost growth and raise those skills levels across the country. We can accelerate our strategic technologies and firmly position the UK as a science and engineering powerhouse, which I think we have been in the past, and we need to get back to that position. So thank you again for listening today. We really appreciate your questions, and have a nice evening. Thank you.